Vectors. Everything you need to know about vectors. Well, we know that a vector is just some kind of mathematical thing that has both a direction and a magnitude. And so it can be represented by an arrow. Obviously, the direction of the arrow represents the direction of the vector, and the lengths of the arrows represent the magnitudes, the sizes of the vectors. One arrow twice as long as another arrow means that the first vector is 2 times larger than the second vector. The other important thing to be familiar with about vectors is components. And so just imagine any vector in some direction, any direction, say this one pointing up and to the left, or in terms of a Cartesian coordinate system, this would be pointing in the positive y direction and in the negative x direction. For a vector like that, any vector that isn't perfectly vertical or perfectly horizontal, you should always think of that vector as a sum of 2 other vectors that we call components. Ax plus ay are the 2 components, and ax is just a vector directly along the x-axis, and ay is a vector perpendicular to that along the y-axis. So as you can see, just using the usual tail to tip rules, if we add ay to ax, we draw ax and then connect ay to the tip of ax. Just a second here, gotta take this. Okay, I can wait on that. So connect the tail of ay to the tip of ax because you're adding ay to ax. And then the sum is represented by an arrow that goes directly from the beginning of this addition path immediately straight to the end of the addition path. And that sum is the vector itself. You can think of the vector itself as basically a sum of perpendicular components. You can also think of the components as like projections or shadows along the two coordinate axes. If you put a screen here, let's lay it out as a horizontal plane, and then the x-axis is in the plane of that screen, and then shine a light down from above, the shadow that A makes on this screen would correspond to the X component. And then similarly, just imagine making a vertical screen parallel to the y-axis, and then shine a light from over here, shine it that way, then the shadow that A makes on this vertical screen would correspond to the y-axis. The thing we want to be able to do is, say, given information about the components, we want to be able to figure out the size of the vector itself and in what direction it's pointing, and vice versa. If we know the size of the vector itself and we know the direction in which it's pointing, we should be able to figure out what the components are like. Those are the processes that you need to be able to do when using vectors. And the way we do it is by noting this. Look at this picture, and you can see that the relationship between a vector and its components is the same as the relationship between a hypotenuse and the 2 perpendicular sides of a right triangle. Right? When you draw this out, showing how the 2 components add together to get the vector itself, you have drawn a right triangle where the hypotenuse is the vector itself, and the 2 other sides, the 2 perpendicular sides, are the components. So that takes us back to a little bit of trigonometry, which once upon a time you saw and once upon a time you were familiar with. You don't need too much trigonometry for this course, but what little trigonometry you do need, you need to know it well. And basically all the trigonometry that you need is summed up in the famous old mnemonic SOHCAHTOA. What this refers to is the fact that you can define the three basic trigonometric functions, sine, cosine, tangent, as ratios of the different sides in a right triangle. So here's our right triangle, H for hypotenuse, O for the side that's opposite some angle that we either know or want to find, and then A for the side that's adjacent to that angle, or rather the non-hypotenuse side that is adjacent to that angle. And then sine of that angle number is simply equal to the ratio of the length of the opposite side over the length of the hypotenuse, O divided by H, and cosine is equal to the ratio of the length of the adjacent side over the length of the hypotenuse, and then tangent of that angle is equal to the length of the opposite side divided by length of the adjacent side. And at one point or another we use all three of those trigonometric functions. Those are the only trigonometric functions we will need. But here's how we use them. Let's say we have information about the magnitude of a vector and its direction. We use these ideas to figure out what the components of that vector are like. So let's take a look at that. So in this case, we know the magnitude of a vector, and I'll always write magnitude, just the size of a vector, like this, just putting the vector symbol inside the absolute value symbol. So we know the magnitude, and we know an angle that tells us the direction in which that vector points. This is also always angle with respect to some coordinate direction, either positive x or negative x, or positive y or negative y, so that in order to completely specify the direction, we have to say that this is some number of degrees with respect to some coordinate direction. For example, let's say we know from this information we're trying to find what the components are like. Let's say we know that the magnitude of this vector is, say it's a displacement vector, and its magnitude is 6 meters, and it points at an angle 30 degrees clockwise away from the negative x-axis. Okay, so what is, draw a picture to make clear what that means. So 30 degrees clockwise from the negative x-axis means point along the negative x-axis and then rotate 30 degrees clockwise. So something like that. And that angle there is 30 degrees. Okay, now we can use these definitions of sine and cosine to figure out what the components are. Here's how we do it. So sine of some angle, and we know this is a 30-degree angle, so we'll use that as our angle in this case. Okay, sine is equal to the opposite side divided by the hypotenuse, or the length of the opposite side is just equal to hypotenuse times sine. And then similarly, cosine of some angle, we'll use 30 degrees, is equal to the length of the side that's adjacent to that 30-degree angle divided by hypotenuse, or the length of the adjacent side equals the length of the hypotenuse times cosine. So in this case, if let's think of our vector A as the hypotenuse of a right triangle where the components are the other two sides, the perpendicular sides. Like that. So here's our 30-degree angle right here. So the side that's opposite to the 30-degree angle is the y component. So the size of this y component is just equal to, it's the opposite side, so it's just equal to the size of the hypotenuse times sine 30 degrees. And the size of the hypotenuse, shouldn't have erased it, the size of the hypotenuse is 6 meters times sine of 30 degrees. And if you ask your calculator what is the sine of 30 degrees, your calculator will tell you that sine of 30 degrees is 1/2. So the size of the magnitude of the y component will be 6 meters times 1/2, or 3 meters. And then the y component is a vector that points in the positive y direction. So we can say not only is the magnitude of the vector ay equal to 3 meters, but the vector itself, since it points in the positive direction, is just plain 3 meters. Now for the x component, the magnitude of the x component just corresponds to the length of this side of the triangle, which is the side adjacent to the 30 degrees. So length of side adjacent equals hypotenuse times cosine. And in this case, the size of the hypotenuse was 6 meters times cosine of 30 degrees. Your calculator will tell you that the cosine of 30 degrees is about 0.866. So that times 3 meters gives you about 5.2 meters for the magnitude of the x component, but the x component of vector A is pointing in the negative x direction. So this is a vector that has a magnitude of 5.2 meters, but the vector itself, pointing in the negative direction as it does, the vector itself, we have to say, is minus 5.2 meters. Okay, now let's look at one other example of this, just to make an important point. Let's say that this time our vector looks like this. vector looks like this. It's pointing in that direction. And again, we'll call it A. And the magnitude of A, just think of it as a velocity vector this time. The magnitude is 10 meters per second. And let's say this time the direction is specified by this angle, 60 degrees clockwise from the negative y-axis. That is, point in the negative y, direction of the negative y-axis, rotate clockwise 60 degrees, and that will give you the direction of A. So this angle is 60. And then use our rules for sine and cosine, almost just like in the previous example, to find the sizes of the two components. So, but in this case, stop and think. Here's our triangle, and the hypotenuse corresponds to a length of 10 meters per second. And there's the y component, and there's the x component. There's our 60-degree angle. In this case, to find the x component, we first have to stop and notice that the x component is a side opposite to the 60-degree angle. So since it's a side opposite, use sine, not cosine, just doing it the other way around from the previous example. So in this case, the magnitude is, using the same rule, this tells us that the length of the opposite side is just equal to sine times the size of the hypotenuse. Size of the hypotenuse is 10 meters per second, and then times sine 60 degrees. And then after your calculator tells you what 60 degrees is, about 0.866, you multiply that by 10 meters per second, and you have, for the magnitude of AX, about, say, 8.7, just rounding it off to 2 digits, 8.7 meters per second. But remember, the y component is pointing in the negative y direction, so the actual value of AY is negative 8.7. You have to stop and check what the directions are. As you can see, it can be easy to skip, easy to forget those steps. You cannot forget those steps. They matter. They're important. And important in the sense that much of what you do subsequently will be wrong if you get the signs of the components wrong. All right, and then the, that's AX. But AX points in the negative x direction, so the actual value of component vector AX is minus 8.7 meters per second. Now, for the sine, or rather the other component, the y component, the y component is on a side adjacent to the angle, and so whenever we're dealing with a side that's adjacent, we use cosine. And so this equation tells us that adjacent side equals cosine times hypotenuse. So let's do that. So the magnitude of AY corresponds to the length of this adjacent side on the triangle, which is hypotenuse 10 meters per second times cosine, because it's the adjacent side, cosine 30 degrees, and turns out that cosine of 30 degrees is 1/2. So the magnitude of the y component is 5 meters per second, and then the actual value of the y component is minus 5 meters per second, because the y component vector itself is pointing in the negative y direction. Okay, so what have we done here? We have used, we started by knowing the size and the direction, the magnitude and the direction of a vector, and then we used trigonometry to figure out the components. Sometimes you'll have to do it the other way around. Sometimes you'll know the components, and from that you'll have to figure out the magnitude and the direction of the vector. So we'll look at an example of that. And the example goes like this. So we know this. And we're trying to figure out the magnitude of the vector and the angle that tells us the direction of the vector. So let's say the x component is 4 meters. It's going to be a displacement vector again. And the y component is minus 6 meters. So we always want to draw a picture when we're dealing with a vector and its components, and that picture will always be a right triangle where the vector itself is the hypotenuse. And so in this case, AX is a displacement of positive 4 meters, and then AY is a displacement in the negative y direction and 6 meters long. And then the vector A itself, which is the sum of AX plus AY, right? A vector is always the sum of its component vectors. And so the arrow representing the sum always goes straight from the beginning of the addition path directly to the end of the addition path. So that's A. And now we want to figure out the magnitude of A and an arrow and an angle that'll tell us the direction. And this angle will work for that. Positive x direction is this way, so A is pointing theta degrees clockwise away from the positive x axis. So it's a right triangle, and we know the lengths of these two sides, so we can figure out the size of the hypotenuse. Pythagorean theorem. The square of the size of the hypotenuse, which just corresponds to the magnitude of vector A, is equal to the sum of the squares of the other two sides. So the sum of AX's magnitude squared plus AY's magnitude squared, or the magnitude of A itself is just the square root of all this. In other words, magnitude of A is just the square root of AX's magnitude squared. Well, AX's magnitude is 4 meters, so the magnitude of AX squared is 16 meters squared. And then the magnitude of AY squared. The magnitude of AY, just the size of AY, is 6. Right? Magnitude is just size without regard to direction. And so the magnitude of AY squared is 6 squared, 6 meters squared, or 36 square meters. So the magnitude of A itself is the square root of 16 plus 36, in other words 50, and that comes out to just a tiny bit more than 7. Say about, when you do the math, it's about 7.1 meters. So this displacement is 7.1 meters long. It's the sum of a displacement 4 meters in the positive x direction followed by a displacement of 6 meters in the negative y direction. Now this angle, and for that angle we, for the first time, use cosine, because remember, cosine is a ratio of opposite side over adjacent side. In other words, in this case, cosine of this angle, sorry, not cosine, tangent. Tangent of this angle is a ratio of the opposite side over the adjacent side. In this case, the opposite side, the length of the opposite side just corresponds to the magnitude of AY. And the length of the adjacent side just corresponds to the magnitude of AX. And the magnitude of AY was 6 meters. The magnitude of AX was 4 meters. So this just comes to 1.5, 1.5, 3/2, whatever you want to call it. So tangent of the angle we're looking for equals 1.5. We want to solve for this number, and to do that, what we're asking is the number that has 1.5 for its tangent. To do that, you have to use the so-called inverse tangent function, which you can find on your calculator. That is the so-called inverse tangent of 1.5 equals something. This thing is the number that has 1.5 for its tangent. That's what inverse tangent means. And so just ask your computer to find, or your calculator to find the tangent of 1.5, and that will come out to about 56 degrees. So displacement vector A points 56 degrees clockwise away from the positive x-axis. All right, that's just about everything that you need to know about trigonometry and vectors. There's one more aspect, which is really just a further, it's not new, it's just further development of some of these ideas that we'll get to next time. But this is pretty much 90% of everything you need to know about vectors for both Physics 2201 and 2202. The trick is that you need to know it very well. You need to be able to do, eventually you need to get to the point where you can do it almost automatically without having to think long and hard about it. Think long, if you need to, think long and hard about it at first, but after practice, and you'll get a lot of practice, it should become a little easier.